So, under certain abnormal conditions such as a DC line fault or a dip in the AC voltage, U can be greater than even 60 degree also considered is abnormal. So, even 60 degree is an abnormal condition. So, let us try to analyze this case where U is greater than 60 degrees and less than 120 degrees. So, what we do is we again try to analyze by considering the fact that each cycle of the AC side waveform can be divided into 6 intervals and each interval can be divided into 2 subintervals. So, one cycle. So, when I say cycle, it is this cycle or period of the voltage or current on the AC side. So, one cycle is equal to 6 intervals, each of duration 60 degrees. And one interval is equal to 2 subintervals. Now, why I am saying 2 subintervals? At any instant either 4 valves conduct or 3 valves conduct. Now, that is true for any value of U between 60 and 120. Okay. So, this range of U corresponds to what is known as 3 and 4 valve conduction mode. So, the previous case of U less than 60 was 2 and 3 valve conduction mode. So, this is 3 and 4 valve conduction mode. So, the first subinterval is the one where 4 valves conduct. The second subinterval is the one where 3 valves conduct. See, this is somewhat similar to the definition of first and second subinterval in the 2 and 3 valve conduction mode also. So, in the first subinterval there were 3 valves conducting there, and in the second subinterval 2 valves were conducting. Now, in 3 and 4 valve conduction we call the 4 valve conduction period as first subinterval, okay. The other one as the second subinterval. Okay. So, suppose the first subinterval that we are going to study corresponds to the subinterval in which valve 3 starts conducting. So, at what instant valve 3 is turned on? Alpha. Valve 3 is always turned on at alpha. So, we have actually defined EA, EB, EC such that valve 3 is always turned on at alpha. Now, this is coming from the definition of EA, EB, EC. Please note that this is coming from the definition. Say we gave some phase angles for EA, EB, EC 150 degrees and 30 degrees minus 90. Based on that, we see that valve 3 is turned on at alpha. So, the first subinterval corresponds to omega OT between alpha and alpha plus U. See, if I take alpha plus U, now U is greater than 60. You are crossing the duration of 60 degrees. See, one subinterval is less than one interval. One interval is only 60 degrees. Okay, let us fill that later. So, if I take the second subinterval in the same first interval, so here omega OT is less than alpha plus 60. But at what instant second interval stops or second interval starts or first interval stops?
U minus 60, alpha plus U minus
Alpha plus U minus 60. Alpha plus U minus 60 degrees. is less than omega OT less than alpha plus 60 for second subinterval. Is that okay or not? Is that okay? Now, what I will do is I will try to redraw this circuit for one interval at a time, say first interval, by just showing those elements which conduct. Okay. Now, if I take the first subinterval, so let me take the first subinterval. So, in the first subinterval, will there be a non-zero current in the three sources EA, EB, EC? Or if I want to ask first, say it is very easy to say that always there is a current on the DC side, ID is flowing, okay, ID is non-zero. Now, which valves conduct in the first subinterval? See, look at the definition of first subinterval. The first subinterval is from alpha to alpha plus u minus 60 degrees, in which 4 valves conduct, and alpha is the instant at which valve 3 is turned on. So, valve 3 is turned on and 4 valves are conducting, means 3 are already conducting. So, which 3? So, 3 is turned on in the first subinterval. So, the other valves which are already conducting are 6, 1, 2. So, that means I need not show 5, I need not show 4. So, I am just redrawing the circuit without showing the elements that do not conduct, that is all. Okay. What about the 3 voltage sources EA, EB, EC? See, when either 1 or 4 is conducting, there will be a current through EA, but 1 is conducting, so there will be a current through EA. If there is a current through 3 or 6, EB will be having some current. They are now both 3 and 6 are conducting, so EB is conducting. So, there is a current through EB, and since 2 is conducting, there will be a current through EC. Okay. So, all the 3 sources and the inductances connected in series with the sources are conducting, the 3 voltage sources. So, the revised circuit which shows only the elements that conduct current is drawn next. So, I will redraw the same circuit without showing the 2 thyristor valves 4 and 5. So, this is EA, this is EB, this is EC, L, L, L. Now, there is a current through EA because 1 is conducting, valve 1 is conducting, this is valve 1. There is a current through EC because valve 2 is also conducting. And there is a current through EB because valves, both valves 3 and 6 are conducting. So, this is valve 3 and this is valve 6. Oh, sorry, I should not short. The anode of 3 is connected to the cathode of 6. Okay. Now, the anode of 3, the cathode of 3 is actually connected to the cathode of, the cathodes of 1 and 3 are at the same potential. Okay. So, this is connected to the cathode. The anode of 6 is connected to the anode of 2. because all the anodes of 2, 4 and 6 are at the same potential. Okay. And the DC side has a current source ID. So, this is the plus positive terminal of the DC side, this is the negative terminal, Vd is the instantaneous voltage. So, suppose I show the current through valve 1 as I1 and I do not give a separate, I mean this is I3 and I3 happens to be equal to ID minus I1 in the first subinterval. So, I am just drawing the circuit for alpha less than omega ot less than alpha plus u minus 60 degrees. So, for this first subinterval I3 is ID minus I1, okay, and this is I6. So, if I take the current through this inductor L connected in series with EB, the voltage source with voltage EB, then it is ID minus I1 minus I6, and the current that is flowing through this inductance or valve 2 is I2, which is nothing but ID minus I6. So, this is the first subinterval. Now, let us try to solve for the currents. So, you see that there are, say I can use the mesh analysis. So, how many loops are there? So, if I want to solve for the currents, given the voltage sources EA, EB, EC and given the current ID, I want to solve for the remaining quantities. So, mesh analysis is appropriate. So, if I want to apply mesh analysis, that means apply Kirchhoff's voltage law to the loops. So, how many loops are there? There are, though there are 3, one loop current is known. So, there is one loop consisting of valves 3, 6 and the current source ID. So, the current ID is known, that is given. There are other 2 loops with current I1, the other current is I2. Okay. So, I can either solve for I1 and I2 or I1 and I6. I mean there is but only 2 independent quantities have to be determined by application of the Kirchhoff's voltage law to the 2 loops. Okay. So, I will just apply Kirchhoff's voltage law to these 2 loops. So, if I take the loop consisting of EB, EA and the 2 inductances and of course, the valves 1 and 3. So, if I take this loop consisting of EB, EA, valves 1, 3 and the 2 inductances L, which are connected in series with EA and EB. So, if I apply Kirchhoff's voltage law, I get L d by dt of ID minus I1 minus I6 minus L d I1 by dt is equal to EB minus EA. Is that okay? Similarly, I take the second loop consisting of EB, EC, valves 2, 6 and the 2 inductances L connected in series with EB and EC. So, apply Kirchhoff's voltage law, I get L d by dt of ID minus I1 minus I6 minus okay, here the current direction is opposite. So, plus d by L d by dt of ID minus I6 is equal to EB minus EC. Okay. So, I am getting 2 equations here. So, there are 2 unknown quantities I1 and I6. So, I have not written in terms of I3 and I2, it is not necessary. Once I know I1 and I6, I can get I3 and I2 because ID is known. So, I will call this as equation 1 and this as equation 2. So, two linear equations, I mean straightforward to solve. Okay. So, solve for I1 and I6. See, if I take the first equation, say if I want to solve, what I need to do is say eliminate one of them. Suppose I take first equation minus 2 times second equation, what do I get? My intention is to eliminate one of the quantities. Suppose I want to eliminate I1. So, first I will solve for I6 say. So, I get 3L di6 by dt equal to EB minus EA. You see that, I mean, see derivative of ID with respect to time is 0, ID is a constant. So, the purpose of this manipulation is to get rid of I1, one of the quantities. So, I get the equation in terms of I6. So, it is EB minus EA minus 2 EB plus EC. So, plus 2 EC. So, this gets simplified to minus EA minus EB plus 2 EC, which is nothing but, what is the next simplification? Minus EA minus EB is, see, EA plus EB plus EC is 0. So, it is minus EA minus EB is EC. So, it is 3 EC. So, I can just cancel that 3 on both sides. So, what I get is L di6 by dt is equal to EC. So, which is root 2 by 3 V sin omega ot minus 90 degrees. So, it is easy to do the integration if I write this as di6 by dt is equal to root 2 by 3 V. I write this as minus cos omega ot. So, solve this for I6. Can I say that this is equal to root 2 by 3 V by omega OL into sin alpha minus sin omega ot
into root 2 by 3 by omega n
into V, root 2 by 3 into V by omega OL
into V by omega n
plus,
I6 of alpha.
okay, sorry, plus I6 of alpha. Yeah, that is correct. How to get an expression for I6 of alpha? Say, I can't leave it like that. I have to write it in terms of other known quantities.
Shall we know that I6 will be going to 0
Ah.
at
The end of first
the end
subinterval.
of the first subinterval.
So, that means I6 at alpha plus u minus 60 degrees is equal to 0.
So why don't we put that?
Yeah. So, if I substitute omega ot equal to alpha plus u minus 60 degree in the previous equation, I get left hand side 0. So, that will give me I6 of alpha. So, this gives the expression for I6 of alpha. Okay. So, once you get I6 of alpha, substitute in the previous equation, you get expression for I6. Okay. So, I will stop here. I will continue from this point in the next class. Then we will solve for I1. So, that completes the analysis of first subinterval. Then we have to go to second subinterval. Then we do further manipulations and get some equations which are similar to the ones that were obtained for the normal operation 2 and 3 valve conduction. Okay. So, the purpose of studying 3 and 4 valve conduction mode is there can be some abnormal conditions, but one difference is we will not get into study of harmonics for 3 and 4 valve conduction mode, because when we study harmonics, what is the purpose of studying harmonic content? Why do we need to study? Why we study? I mean, if there is harmonic content, we know there is harmonic content. We want to know what is the amount of harmonic content. Okay, knowing that, what next? What do we do with that? Why do we want to know?
Because we need to eliminate.
Eliminate how? Yeah. So, finally, we will use that to design filters. So, when it comes to abnormal operation may be existing for a few seconds or a few minutes in a year. So, for abnormal operation, we are not going to minimize harmonics. It's actually not eliminate harmonics, minimize harmonics using filters. So, filters are designed to minimize or reduce harmonics. So, we are not going to worry about some abnormal conditions which may exist for a few minutes in a year. Okay. So, what we are bothered about, normal operation. So, harmonic analysis is done only for normal operation, because we are going to design filters only for normal operation, not for abnormal operation. Okay. But we need to look at a few other quantities when it comes to abnormal operation. So, only those things we will be doing. So, obviously, we will not be doing any Fourier analysis for abnormal operation. Okay. So, normal operation itself, I mean we have, there is, it's sufficiently laborious. I don't know if you have tried, you would have noticed that. Okay.